I have seen your email a minute ago, and will answer sometimes after the meeting. So, very happy to see everyone connected. So it will be a collaborative meeting with research group of Professor Rasulev, and main speaker today is PhD candidate Meade Erickson. So he's doing very interesting calculation, trying to describe the experiment on photodegradation when sunlight can destroy packages, plastic bottles, and make it more environmentally friendly. Hopefully he will tell more about this. And it is, he's trying to apply the computer code written and debugged by Dr. Han, who is also part of this meeting. So the idea is that during and after presentation, we can collectively discuss and provide healthy feedback that can iteratively improve the work and make it brilliant. Okay.
Thank you for the introduction, Dr. Gillen. So I don't know if you guys can see my screen if I'm the biggest one, but do you guys see what I have shown here, the title?
First we did, and now we see.
But it's just switched off.
When you start speaking, it disappeared. Please try to share screen once again.
How about now?
Okay, we do see it.
Good, good. Okay, so I just want to start off by thanking Dr. Killen, especially. Him and his team have been extremely helpful in the work that's been produced so far. And with his guidance, it could not have gone to as far as it has so far. And then also I need to thank my advisor for allowing me to do this and helping me as much as he is able to. And then Dr. Han as well. His code has been able to assist us along the way, which is greatly appreciated with all three of their help. Okay, so I just want to kind of give you guys an update of what we're doing. If it's the photodegradation of optically active polymers. Okay, so time-dependent excited state molecular dynamics of photocleavable nitrobenzyl group, serving as a photo-triggering polymer building block. In this particular work, you'll see some compound that you guys may have read from previous work of other NDSU members. So I do want to just give a kind of quick overview of what exactly are we doing, just a conceptual idea. I'm going to be using this method called time-dependent excited state molecular dynamics. And the idea is you excite the electron from its original orbital into an excited state, which transfers it to another orbital, and de-excitation, which goes from that excited state and getting rid of energy, and it's being reduced into its original, let's say, orbital. I wanted this graph here on the right is just kind of a comparison of different techniques. So on this top portion, it's molecular dynamics, which you stay in the ground state, but you increase the energy throughout your simulation. And then excited state molecular dynamics is it increases from ground state to excited state, but stays there. And then TDESMD, which is time-dependent excited state, we go up to the excited state and then go back down. Just like this diagram over here, we're exciting the electron and the de-excitation. Just kind of a more mathematical view of it. This excitation and de-excitation process is called the Rabi Cycle, which is based on the Rabi theory. It's the cyclic behavior of two-level quantum system in the presence of an oscillator driving field. So in our case, that driving field is light, is the equation being used. And gamma is the frequency, Rabi frequency, which is related to the transition dipole intensity of the electric field. And how that relates to us is transition dipole relates the ability of a system to be perturbed by light. So this equation connects Rabi cycle into the ability of the transition dipole to perturb light. or excuse me, to the system to be perturbed by light. Okay. So so that was the computational approach, and now we're going to look at more of the what are we applying it to? And the compound that I've highlighted here in red, members of NDSU such as Dr. Webster and others have developed a compound that was able to be generated, polymerized, and then once it was UV light was irradiated onto it, it was able to be decomposed and then recycled. So the monomer building blocks were able to be reused. And so we wanted to take a closer look computationally to see how this degradation can occur. During part of their experience, they showed a color shift with the irradiation.
Meade,
and we believe that...
Meade, would you allow questions to be asked in the middle when you speak?
You can if you'd like. I didn't know how this set up, if it was going to be more casual where they can interrupt me, or it was supposed to be kind of more official. So I'm open to either view.
Okay, thank you. Can you please teach at least me, maybe some other in the audience, how to call this compound? You are giving these chemical names, but some basics of chemical namings, like which part it's like how do you assign namings and which parts are splitting on the pieces. So like what is 3-formyl, what is nitrobenzene, what is furan? Can you just quickly go over?
Oh, okay. Yep. So the furan group would be this oxygen, this pentane with oxygen at the tip of it here, and then nitrobenzoyl is NO2 with these carbon, let's just say extensions on the edge of it with the benzene here. So nitrobenzene, the extensions, and then formyl, I believe, would be the connection between them, but I actually don't know off the top of my head exactly what formyl is. So like, if I am correct, it would be the carbon oxygen, oxygen into the furan group.
Okay.
So, okay. Like I said, once again, okay, if we're going off that, you guys can ask questions at any time. Please interrupt if you'd like. Once again, to go through the irradiation, there was a color shift from clear to this opaque orangish color due to the irradiation. We believe it was due to the cleavage of these bonds, as you can see here in 7AB, between the oxygen and the carbon in the formyl group. So I know it's kind of a jump straight into the computational portion, but generally we start off with the density of states. It's kind of showing the occupation of electrons. Where the heck are all the electrons? Well, we want to look at this position, which is the HOMO-LUMO gap. HOMO, which is the highest occupied molecular orbital in ground state, which is orbital 112 here. And then there's a HOMO-LUMO gap, it's an energy barrier, to an unoccupied portion. So I just wanted to show an example of the density of states, or excuse me, the orbitals themselves of 112 and 116, and they show some importance later on. But for some of you who may not know, if you excite, remember I believe it was the first slide I showed, you can excite an electron and make it jump to different orbitals. So in our case, we were going to be jumping, let's just say, from 112 to 113, or from 112 to 116, and that excitation, or that jump helps us determine what sort of degradation could occur, that we can find some sort of trends depending on where the orbital was taken from and where the orbital is going. So I know I'm making another quick leap here, but in the previous slide I showed differing orbitals from where the electron was and where the electron's going, and through I believe oscillator strength we were able to narrow down kind of where this transition would occur more frequently. So for example, this is clock, we're going clockwise, least to greatest in the clockwise direction. So in the original case, the electron is in orbital 111, and it jumps to 114, and it has approximately a transition energy of 2.755. And 112 to 116, obviously you can see is quite a large peak here, right there. 110 to 116, we go down to 3.5. 105 to 160.
I have a question.
Yeah, of course.
Sorry. The transitional energy, the orbital energy, the 2.7?
Yeah. Yep.
Why is that significant?
Why is it significant?
Mm-hmm.
We are trying to determine at what leap from electron where it was occupied to electron where it's unoccupied, that leap to occur. This energy is an indicator of how possible that is. How much energy is needed.
Right, but does this, if you can extend a little further, I mean, is this a lot? Is this a little? Is this good? Is this what we expect to see? You know, those kind of things.
That analysis is still being underway. So, like, just due to timing, I can only show kind of the results that we have. And actually, part of my goal is actually to find some sort of trend, or at least analyze. Oh, is the 2.7 important for this 111 and 114? Is this 112, 116 important with 3.2786? So I have to be able to still analyze that, and that's just due to timing at this moment.
Okay, gotcha.
Meade, can I contribute? Can I contribute to the discussion?
Please do, Dr.
Okay,
Keller.
yeah, thank you. So there is, it's not a big hope, but potentially one can anticipate that this system may exhibit some unique properties, and Meade is meticulously checking several options. So the question was why the transition energy is important. So if it is important, if the response of the system in a sense of chemical reactivity depends on transition energy, then it means that photo decomposition will be color selective. For example, you drink a beer, you have two, or whatever, soda, you have two plastic bottles in front of you, and then you have two laser pointers. You shine laser of red color on one bottle and blue laser pointer on another one. The one with red color stays intact, and the one you irradiate with blue explodes. I'm exaggerating, but it could be an outcome if such sensitivity exists, and therefore Meade is trying to meticulously try different transition energies for excitation.
Basically where he sees the pronounced difference, where he sees the pronounced effect, to give him, you know, kind of go along what he think might happen in this system. Okay, thank you.
Thank you for your input, Dr. Keller. Does anyone else have a quick question at all?
Yeah, I just have a quick question. So what do those red X's on your model represent?
Yep. So I do want to, I just didn't get to that point just yet, but the red X's are actually, you'll see in a quick part of this presentation, you'll see videos of actually this cleavage occurring. So these X's are kind of indicating that cleavage did occur. And so obviously a unique thing that we would see is this 112, 116, you would see it as a high peak as well as quite a large amount of cleavage that occurred, just visually. Okay. Okay, I think we'll go to the next slide. So I apologize for this deformed figure, but the information I'm going to be showing is the next few slides are going to be going off the next mass spectrum information. So just for a quick example, we have carbon, which, we have O2 or oxygen. So 16 is the atomic mass of oxygen. We have two of them, so that would give us 32. As you can see in my scale here, it goes from 0 to 50, and 32 is approximately in the middle. So we would believe that O2 exists with the information. And, example, nitrogen, and then the NO2 right here. So with value of 46, we would indicate that that exists. And so in the future slides, I know I mentioned how the video, you would see a video, and also you'll be seeing this mass spectrum information as well. So in particular, with the paper that I had brought up with like Dr. Webster and the others of faculty of NDSU, belief that we have is with those specific bonds that we saw breaking in one of the original slides, there would be two like generalized products that we could see. So in one case, it would be this furan with 2 carboxylic groups. So we have this general figure down here, and it's going to have that atomic mass of 148, as well as this nitrobenzene with 2 CH2 linkers of 149. And so hopefully in the next few slides, we would be able to see that, because that's what we proposed that would be one of the bonds that would be breaking. Okay, do a quick video.
Meade?
So,
may I ask?
Yes, Dr. Kenny?
So when you are running video, would you help us to interpret it and navigate our eyes to a right fragment? You do have some labels, and it's quite a big molecule. Where should we look at?
Yeah. Yes, of course. Yep, I wanted the video to go once and just kind of to visualize it, and then I would explain everything. And then, I don't know, we could probably go back just a hair and redo it. There's actually going to be 8 videos, so I kind of wanted to take time on the first one so we can analyze it. But yes, I planned on doing so. I just didn't want to talk while the video was running. But in just for future cases, what you'll see here is the compound that we're looking at, and then I have indicated where I saw a noticeable bond breakage. So in the video, you may see bonds kind of joining and rejoining, and that is just more like bond stretching, right? And in this particular case, I have the bond lengths set to 1.6. So if they exceed that, you see the bond just disappear, 1.6. And if it comes back towards it, obviously the bond, if it goes to 1.5, the bond will exist again. But there's more of this oscillation effect, but once again, the red X indication is more of a large break, let's just say beyond 2. Oops. And on the far right here, I wanted to once again show you the mass spectrum information that we have. I wanted to highlight, remember what this nitrobenzene group with the 2 carbons at the connection points, it would be about 149. And then 158 would be this furan group with the extensions on it. And in this particular case, 111 and 114, it shows that it may exist, this N group here. And part of this presentation, the goal is to try to compare to other orbital jumping from its original state, from its original orbital to the excited state, which is the other orbital. So in our case, it goes from 111 to 114. As you can see here, the mass spectrum is showing smaller fragments that do occur. I didn't have time to look exactly what this, peak would be. Just by going off of it, it's 12, which would be carbon. But relative to our video, it seems as if we still have all our carbons connected. So it's quite just a slight differentiation between the mass spectrum is showing and what the video is showing. Okay. I did want to show you guys the transition energy and oscillator strength for this particular case. And we'll go to the next slide. And this is where what seems to be large degradation occurs. You can see a lot of initial bonds breaking from this compound shown on top. oops, go to here. So I don't know why it's there. Okay. So as you can see, I wanted the bonds that I have indicated here with the distance between them. They currently are the original bond linkages that we thought would be breaking down. And so on all the videos, you should actually see that in white text here what that bond length is, and it should incur these types of molecules if the bonds break. So looking at this 5.4 distance, that would be this X right here. And then I wanted to emphasize that it seemed to create the CO2 unit, which I have drawn in blue here. That's what you guys would see in this unit right here. And then regarding the mass spectrum, as you can see, large number of different fragments did occur, where at approximately 46, I believe I had, I apologize for not showing it here, but I believe I did have a unit that had an approximate atomic mass relating to this peak, and I apologize I don't have it shown. But as you can see, this is quite a large difference between this last degradation simulation. And the transition energy is larger, but the oscillator strength is greatly larger, between 0.49 in this particular case to 0.16. The interesting thing about this case too as well is you see the furan group kind of open up in this area, which I would have thought would be highly unlikely to occur, but yet you'd see degradation to occur. The furan group opens up quite largely. This next slide, TDESMD 110-116. The transition energy between the last one and this one is very similar, but the oscillator strength is quite a bit different. It's greatly reduced. And we would see this nitro, the bond between the nitrogen and the carbon of the benzene group does break off. And also that original bond that we would have believed to have been one of the more common things to break relative to the experimental data, we see that it only breaks in one position rather than multiple throughout the chain or compound. And in our particular case, we do see a small, let's just say, amount of these two compounds. As you can see, I have in blue, and green. So we would believe that part of the products of this particular simulation produces that. In this simulation, less degradation occurs, but also it's just in a different portion of the compound where the nitrogen and the carbon bond break. It may be hard to see, but it's coming at us. Okay, next one. Interesting enough, it seems to be a lot of the degradation only occurs in one portion rather than throughout the whole extent of the simulation. So in this particular case, we would see these three X's indicate bond cleavage over here. I want to posit here, as you can see, the furan group had not only opened up, but has been coming towards us in the viewing. And the bond that we actually believed would have been broken would have been where my mouse is right here, this carbon and this oxygen here. And it obviously did not occur. It oddly enough, it occurred closer to the furan group.
Could you explain why?
Once again, it goes back to the timing of the analysis. I apologize. I do not. I'm still trying to figure that out myself. This is just the information that we've gathered so far, and then the mass spectrum data indicates this. And so the goal is once I find these trends or that information, like Dr. Killen had mentioned with the transition energy, I can actually I could explain exactly why or what we believe would be making this occur. And I just haven't been able to do that just yet.
Okay. The X's indicate where it was cleaved, correct?
Yep. So like
I wonder if that ring strain too would be a part of at least one of your interpretations.
Say that again.
The ring strain in that cyclic group. might be part of your interpretation.
Yeah. Like, I mean, so for example, like the electronegativity of like oxygen relative to just two carbons connected or carbons in the benzene ring are obviously going to be different. You know, there's going to be different dipoles, different information. And so like part of it is, you know, how do we, other than looking at bond strength, what indicators can we use to determine why is this bond breaking before others? So for example, my belief would be the oxygen, just casually viewing this, I just would imagine like an oxygen carbon bond breaking first, but that obviously isn't always what's occurring.
Meade, may I contribute to the discussion? Meade, may I contribute to the discussion?
Say that one more time. Keep going. Is that what you suggested?
May I contribute to the discussion?
Of course, Dr. Killen. Yes, you may.
Thank you. Thank you. I'm going to throw in one of the directions of thinking, one of the hypothetical explanation why specific bond is being broken. But what I'm going to say could be wrong and needs to be proved right or wrong through numerical experiments. When photoexcitation from one orbital to another one has a charge transfer character, when photoexcitation moves electron and hole away from each other in space, the groups which contain this positive and negative charge may experience attraction, and the bonds will be attracted closer to each other. When one de-excites back to the ground state, the bond will become loose. So there is a chance to find correlation between degree of photo-induced charge transfer and cleavage of a specific bond. Done with the comment.
Thank you for your input again, Dr. Killen. Does anyone else have any questions at this time? Okay. In this particular case, we'd actually see from 109 to 121, we see that the fragments that we thought would be existing doesn't occur at all in this particular simulation. But yet we do see in the simulation itself, we do see one of the bonds breaking here that we thought would occur. I have the length shown of 2.39 that goes over the 1.6 limit that I had previously mentioned. The oscillator strength here is 0.17, and as these simulations are going on, I do want to mention that the transition energy is increasing throughout these. So the original one that you guys had saw was the lowest at, I believe, 2.7, and then it goes up to about 6.5. And so this is the last simulation that you'd see. This one obviously has, let's just say, less total fragments compared to some of our more excited ones, but yet they're more intense. Same with this one, 93, 118. The scission would occur near the center. It should be this, let's just say, bond length here. Now, what I want to kind of mention too is though we have the peaks that I have put here are more like a visual representation of where I would believe that this this group would be and this group would be. I mean, if they're all within 1 or 2 units away, that's 1 hydrogen being added or not added. So I think we could be somewhat, let's say, not vigorous on saying that this exists or not, depending on where this line correlates. Obviously, the units that right here, where if it's the green line in this particular fragment exists, if there's an extra carbon attached to it, it would shift to approximately here. So, we could correlate that sort of fragment still exists. It's just with 1 added unit next to it. And I believe this is the last one. What I did notice here, looking through the slides, is as oscillator strength increased, we did see more number of, let's just say, different fragments, this oscillator strength. So in the original one, we only saw maybe a couple large peaks. But now, as some of our more extreme cases where more fragments occurred, our oscillator strength was higher. And I just would like to kind of end with a quick conclusion, just saying the largest amount of degradation occurred in, that 112, 116, 112, 122, 109, 121, 93, 118, and 91, 121. Once again, I know it takes more time for me to analyze and show exactly kind of the huge strengths and, the correlation between the sort of fragmentation we would have seen and the oscillator strength and transition energy. And so it just takes more time. So that's what I have so far. I thank you guys for listening and viewing what we have. Okay.
Okay. Please join me.
Any questions so far?
Join me in thanking Meade for interesting presentation.
I do.
Yeah, sure.
Thank you. Thank you.
And
great work, Meade. So I appreciate that. I do have a quick question. If you could kind of give a little bit more on the motivation, a little bit of background. Say particularly, I've never seen this system before. Like, could you go back a little bit and explain why you're interested, what you hope to see, what you hope to gain, and what would be the benefit of looking at this system? If you can give a little bit more detail on that, I'd appreciate it.
Yeah, the cool thing about simulation is seeing the intermediate steps, or what's called the mechanism. So when it comes to this particular molecule and it being degraded, and you seeing what the outcome could be in real time, let's just say that's an hour between you and putting 6 hours of UV light on it, and then actually going test what are the end results or the products of that UV radiation. You only see the beginning and the end. What happened before irradiation, what happened at the end. But what we get to do with molecular dynamics is we get to see what's happening in the middle. What exactly is occurring in the middle. So that, let's just say, in-depth look helps us understand exactly how degradation is occurring, and that may help us further along the line develop better, more degradable monomers or polymers.
In what application would you use this system?
This particular molecule, let's just say this compound, if you're talking about system, do you mean the compound?
Correct. Okay.
Their paper had just kind of shown this proof of idea that you can make a polymer, you can, photocleave it with UV radiation, and then reuse the monomer units to make another polymer. And so it not actually is necessarily used, let's say, as paint. It's just it's just a proof of concept. Right? And so that's what we wanted to do, is look into exactly how this is occurring and what exactly is happening.
Okay.
Good. Thank you for your questions. It's good to hear that you do.
Meade, I have a question.
Yes. Yes.
So, in overall, was you able to kind of put in a preference what the bond degrades first and what bond degrades second, and then the third one? Was you able to find that kind of dependence, let's say, or relationship?
Not yet. My understanding is that what we'd have to do is throughout these differing simulations of the mass spec and videos, we'd have to compare with what's actually happening in real life, and then you can determine, let's say, which one of these simulations best replicates what's happening in real life, and then you could get information from that simulation. But that is something that hasn't occurred yet. So no, I couldn't determine what exactly bonds are breaking first or why by any means. I don't have that information.
So this intensity of peaks, which are kind of showing the probability of this particular transition, not really correlates with the what's going to break first or the second, right?
Yeah, this is more like the end product. As you can see here, the video is more of what's happening, you know, in the middle or during the process.
Mm-hmm. Maybe it's also a question to Professor Killian. Is that how it's how accurate we can predict what bond is going to be broken first or what bond is second? Can we say that from our calculations, Dr. King?
Yeah, Professor Rasulev, there is a good hope that this question can be answered with results that Meade has already computed. One needs to do more steps in processing of this data. Specifically, one may want to monitor the bond length as function of time and plot several bond lengths on the one panel and compare which one breaks first, which one is second. In addition, one may want to interpret some of the smaller peaks not as the event of final bond cleavage, but as temporarily increase of the amplitude, as oscillations of high amplitude. So one needs to be careful and apply intelligent interpretation of this data in the mass spec.
I see.
They are tuned to be very sensitive, and one can either change this tuning parameter or like if there are tall peaks, then for sure it is definite bond breaking. If it is lower intensity peaks, it could be just I wouldn't say noise. It could be a reflection of high amplitude oscillations, which are recombining back into the intact bond.
Okay, I see. And then connected with the same stuff that the question. So the mass spectrum what the Meade shows is kind of pretty simple, I would say. I mean, they're only kind of final, the smallest fragments visible over there, but not like intermediate fragments.
There are intermediates. The next time, when we will do iteration and Meade will present once again, the methodology section should be blown up, so to say, extended with more details. And the protocol that Meade is following, and based on computational programming by Dr. Han and by yourself, makes an average over the whole trajectory. So if there is a short-lived intermediate with a specific mass, it does contribute to the mass spectrum as well.
Yeah.
So in some sense, it is an ensemble average over a reaction, over like ensemble of reactions which went to different stage of degradation.
Yeah, that's what I was expecting, kind of to get this kind of average at mass spectrum.
It is.
Has all the fragments which you're getting through the trajectory.
And therefore, there are so many peaks.
I see. Okay. Okay. Interesting. So just based on these, the intensity of these transitions, we cannot be 100% sure that the one which has the highest one has the highest probability for the breaking at this particular bond. We cannot say, right?
We can. The height of the peak correlates with lifetime of intermediate or the product or reactant. So if it is a short-lived fragment, so if it is either short-lived intermediate or if it is a product that has been developed at the last stage of the trajectory, then it will be low intensity peak. If the product has formed at the beginning and will stay unchanged for the whole trajectory, it will be very tall peak.
I see.
And after, I want to hear your questions first, and then I will ask technical question to Meade in this respect.
No, that's all the questions I have at this moment.
Meade?
Yep.
So, what is the total atomic mass of the overall polymer?
I believe it is 606.
Why your range goes from 0 to 400?
I wanted to show, let's just say, fragmentation specifically highlighted in this area, in this region. If I would have extended it, it just would have gone, let's just say, would have scrunched the peaks a little bit more. And as you would know too, is if fragmentation occurs in the middle, you would have 2 units at approximately 300. So it seemed unnecessary to always go beyond 400 units.
But for all of us, for the audience to understand what you are doing, can you please verbally describe how would the mass spectrum look if your range would be going from 0 to 700?
You would see if let's just say if degradation didn't occur, you would see one large peak at 606, one very large peak. But since the videos I've shown degradation, you would see quite a large flat line beyond, let's just say, the 400 mark. And so that is why I just wanted to show from 0 to 400.
But would you agree that the peak at 600 something would be present for all trajectories? Just for those with intense degradation, the heights of this peak will be lower.
I would agree with that, yes.
Okay, very good. Let's ask for more questions. And if someone is not comfortable speaking it out loud, it is very welcome to type in the questions in the chat line.
I have another question. So, what are your future plans to address some of the things that we discussed here in terms of why you're seeing what you're seeing, and what is the main take home of this? Like, what is it you still need to do?
Yeah, well, though it was not brought up in this discussion, this conformation that you see has been, let's just say, twisted to a certain conformation, okay? And what we're going to do is actually, there's another different conformation that we've done this similar methodology, and we've applied it to that. And what we still have to do is compare the two to see if that conformational change changes, let's say, the outcome of the mass spec information. So we need to do a comparison between these two different conformations, which I did not go over. Okay, and then regarding what you're asking about what my future steps are, or what my plan would be. For example, I need to determine what sort of visual or numerical trends are present regarding high and low degradation. So then we can use that information maybe to extrapolate further, or to determine internally what exactly is happening, to find those trends. So, for example, I only showed these homolumo orbitals just for this one particular case each. As you can see, a common thing is that you'd see these orbitals focusing around the furan group. In other cases, you may see it around the benzene or other areas with different orbitals.
Why does that matter?
Why does it matter?
Yes.
Well, what you find that trend, there'd be some further analysis. I personally do not have experience on knowing, like, let's say the orbital is, in our case, it's 112, right? And we're saying the orbital is around this furan group. Now, let's just say it was around the benzene group. I don't know why exactly that difference does occur or why it matters necessarily, but I know if there's a trend there, and then I can look further into it. Maybe Dr. Killen knows.
Well, would that be related to your charge transfer?
Mm-hmm.
And your energy? Availability of electrons?
Possibly. Meade?
Yes.
Would you, right now, your cursor is showing on one of the carboxylic acids for the orbital, for the occupied, for the HOMO, right?
Yep.
And it has p orbital on the oxygen with double bond. Can you focus your cursor there? Not furan, but
right here. Yep.
the oxygen that it doesn't go further to connection, that it's standalone double bond.
Yep. Do you see my mouse?
It delays a little bit. So what is the amount? Is there any population, any density on this oxygen?
Oh yeah, obviously.
Okay.
With the electron
Now,
cloud, yeah.
would you please point your cursor to the same nucleus, to the same atom for the unoccupied orbital, for this 116? So is there any change in the shape,
you can see
and amount?
The cloud obviously changes size, yes.
So hypothetically, it needs to be checked, but if the cloud increases, it means there is a charge transfer to this oxygen, and then the bond between this oxygen and the carbon becomes more loose, or so it feels this change in the electronic configuration. And if one goes over several events of excitations and de-excitation, it may accumulate strain due to this electrostatic interaction.
Meade, could you explain the difference between 116 and 115?
You mean, like in what way? I mean, I don't have the orbitals picture shown, so if we're just looking at the dead groups.
What's a special, like, I look at 113, 114, and 116, and they seem kind of similar to me, but what's special 116 versus 115? Why pick 116?
Just looking at our diagram here, we could see quite a large degradation occurring. So, just looking off the video, we specifically chose 116 and 112 because that sort of homolumo jump, or excuse me, that sort of electron jump between those two orbitals showed some sort of large excitation.
So in some sense, Meade is showing reverse engineering. first he found which transition gives most vivid result, and then he is showing which orbitals contribute to this most interesting result. But ideally, one needs to go through meticulous exploration of all orbitals and all transitions and try to identify correlation between shapes of occupied and unoccupied and outcome of the chemical reaction, photoreaction.
So generally you would see all these figures for each individual orbital. I just showed these two for visualization because I haven't had time to analyze each individual orbital and its simulation.
Meade, I have another question.
Mm-hmm.
So you were talking about, in real life application here, we have a coating, right? And we're looking at the degradation, right?
I can't say it was a coating. As you can see, it's more like a resin.
Okay, it's a resin.
Okay.
And we're looking at the degradation. Have you thought about the time aspect of this? And how would that relate to what you're doing to real life studies?
Well, the connection is we're kind of seeing what's happening very quickly. Obviously, we're in the femtosecond range. And so we cannot relate femtoseconds to 6 hours. That's just not possible. So with the time we do have computationally, we're just looking at what's happening in that small amount of time with large intensity light irradiation, or that excitation, de-excitation, excitation, de-excitation, rinse and repeat. That block of information we can use, let's just say, for comparison of future molecules that we use this system upon. So
let me rephrase my question. Maybe my question wasn't quite as where it needs to be. How long does this resin last in real life before it degrades?
Remember, this is like high intensity UV light. So like in a casual office setting, I mean, it would just be this irregular before irradiation.
What would you be using it for? What real application would you be using it for?
Well, yeah. So, okay, let's go beyond this. If we can figure out what sort of trend, at a compound level, we could apply that into future monomers. We could incorporate those, such as say a photo trigger. Right? That's what this is kind of going off of. If we understand at deep level why exactly photo triggers exist and how they work, we could possibly make more photo triggers that are easier to make, that they're cheaper, and we could implement them more into polymers at a cheap and reliable and productive manner. So the goal is to say, okay, we know this thing degrades right now. How the heck is it degrading? How exactly, what mechanism, what exactly is occurring? And so us looking at this deeper level, we'll get that information, and hopefully we can use that information to create more products like this. So that's the general view. And then if you're asking particularly what happens with this particular resin, this resin that I have shown on the paper was just trying to show a proof of concept that you can irradiate light and you can get the pieces that are broken or the monomer units that have been broken from the original polymer, and you can reuse them. It's like recyclable. And it was all done because of a photo trigger. It was initiated by UV light because of this nitrobenzyl group.
And it sounds like that's an easier process and less expensive than, say, actually recycling it in solution.
Yeah,
but polymerizing it, which is a much harder process.
Well, I mean, whether it's cheaper or not depends on a lot of factors, but it's a possible, let's just say, alternative to biodegradation or thermal degradation. This is like one way of degrading a polymer, and maybe you could find a way to have just sunlight break it down, or there's a lot of other possibilities beyond what I'm showing in this particular presentation.
Right, but those all kind of are different processes, but yeah, they have kind of a similar theme to them.
Yeah.
Okay,
Yep.
thank you.
Yep.
Okay. Are there more questions? Oh, someone is typing a question. Let's check the chat.
I just
yes?
have a comment, just to continue the discussion. In this particular paper, the scientists just wanted to create a polymer which can be degraded at the time they want. So photo-triggered the polymer. So it means they just make an object, let's say bottle, from that, use it to some extent, and then when they decide to degrade it, just irradiate light of particular wavelength. So it's not just sunlight, it's a light of particular wavelength. In this case, it was the UV light of particular wavelength. To just degrade it within a few hours and then reuse it. So that was the main idea of the scientists in this particular study. What Meade wants, he just wants to extend it. He wants to find the ways how it's possible to predict the degradation using the molecular dynamics methods for many other types of the polymers, not just for this one. And then make some kind of predictions for many other kind of polymers, how quickly it can be degraded and what kind of the light needs to be irradiated to them in order to degrade them. In regard of the timing, how quickly it can be degraded, that's another question, and that needs to be probably investigated with some other methods, or like in addition to the molecular dynamics what we are using. Yeah.
Thank you for your input.
So, and someone was typing a question?
It was not a question. David Graupner looked through the paper of Dr. Sivaguru Jayaraman and typed a quote from there explaining the impact of this research. So in some sense, it goes what we verbally addressed. I can read it out loud. Our proof of principle strategy has shown that one can successfully append triggering units to monomers derived from biomass and recover them after degradation so that the monomers can be reused to minimize impact on the environment, making the process both green and sustainable.
Meade, just a comment. I think this would be excellent to paraphrase this as your first slide going into this, because I think it's beautiful. It encompasses what I think would be quite useful, and no one would question it. Just a suggestion.
Yeah. It's hard to know exactly what needs to be explained better. Yeah, so this is why we're here, right? So to get comments from you guys. So thank you.
Meade, I have a little bit silly question. What would be your definition for criterion of success for this project? At which point you would say, oh, okay, it is great results, enough doing computation, let's deliver it to the general public?
If we could relate the mass spec data that we got to experimental data, have it somewhat relatable. So for example, other papers have shown that this mass spec information I have provided can be almost overlaid over experimental information and be very similar. So in our case, that would be great to have that sort of correlation or connection between experimental and computational data. And then also understanding the mechanisms of exactly why this degradation is occurring regarding the particular wavelengths that we are, or intensity of light that we're introducing onto the system. So those would be kind of my two criteria. Once again, is to compare experimental and computational, see if they can be correlated quite well, and also understanding the mechanism at a deep level. Yeah.
Okay. I applaud, and it is really wise criterion of success. Let me constructively criticize it.
Please do.
So, do you see a lot of experimental papers, a lot of experimental results providing mass spectra of the degraded polymers?
How about this? I don't believe there's the specific type of spectrum, which is time of flight. That is not being produced as much, I have seen, on degradation of polymers in papers. Because the particular spectrum that we're looking at is the time of flight. And so I don't see that a lot in papers.
Okay, and in this paper, Angewandte Chemie, what are the characterization tools? They characterize the brown liquid after it has depolymerized by several characterization methods. What are they?
For example, TGA, HNMR, they don't use this particular mass spec, let's say, characterization technique that I have shown. But they do use others. I apologize, I don't know all of them off the top of my head, but it's like TGA, HNMR.
What else?
I want to say, oh my gosh. I know the acronyms are not coming for some reason. I apologize. It's been a bit since I read that article.
Do not worry. Do you remember? Well, and the question is not about the paper, but about supporting information, which is much more detailed. Do they show infrared spectra?
Oh, yes, they do. They do show information regarding infrared spectrum. Yes.
So, do you think it is possible to take product simulation cell of your reaction and compute infrared spectra?
With your guidance, anything's possible, Dr. Killen, of course.
You are too kind, but indeed it is possible to find normal modes and do infrared spectrum. Also, you can do it without anyone's help, the UV absorption spectra. So can you go one slide back? One more back? Yes. So for the, the one with test tubes. So what would be the difference in the UVV's absorption spectra of this test tube before radiation and test tube after 6 hours?
I may have the wrong verbiage, but I know there's a shift. I would say a red shift, but I may be wrong with that sort of verbiage. But
that's good. That's good. Red shift of what?
I want to say color, but that's probably the improper.
So the homo-lumo gap will be less, right?
Say that again.
Homo-lumo energy gap.
I don't want to say yes because I'm not 100% sure.
But absorption's first peak in the absorption spectrum is shifting to the red, as you did mention, red shift.
Okay.
So one of the potential criterion of success could be absorption spectrum, not before the reaction, which you have already shown, but absorption spectrum after the reaction. And if it does show red shift, it is criterion, maybe not 100%, but it is partial criterion of success.
Okay. Yes, we could do that.
Are there more questions from attendees, from members of?
I believe that was David. Go for it.
So I'm sitting here looking at the paper you're citing.
Okay.
And if you want to go to the slide with
slide with what?
The model. I think it's 2 slides from this, if I remember.
When you say model, are you saying simulation or
the one where you have the chemical thing itself? Yeah, that one. So I'm sitting here looking at that paper, and you appear to be built this off of their Model 8. My question is, in your model, you appear to be using nitro groups instead of nitroso groups. Is there some reason that you're switched that?
Nitroso? NO2? Okay, what do you mean by so? What's the so
if
differentiation?
If you look at your chemical name, it says nitroso.
Okay.
Which is NO. You have NO2s, which is nitro.
Oh, okay. I apologize.
I'm just wondering if there's some reason you switched that.
Yeah, so in their thing, they have NO2, is that correct?
So they have NO2s in models 7 and 9 and basically every one except model 8, which appears to be the one that, or chemical 8, which appears to be the one that you made the model of.
Well, hold on. So like I have the picture shown, which is number 7, which is NO2, right?
Yes.
And then obviously I have a picture here in the black section, which is NO2. And then you're saying that's different.
Yeah. So it appears that you made or chemical number 8. You have highlighted chemical 7.
So what is the difference between 8 and 7? Because I don't have 8 on here, obviously.
So the basic difference is that you lose one of the furan groups, and it's a nitroso instead of a nitro.
Okay, so you're saying like I have a benzene-furan, right? So you're saying one of these groups is taken away, completely gone.
So basically, right where your pointer is, you
Yep.
would cut right there, pretty much.
Yeah. Okay. Yeah, so there is some, let's say differentiation. So, I mean, the goal is, if you think of a polymer, it's going to have this repeat symbol, right, of benzene, furan, benzene. That was kind of our, let's just say reduction of the system. So we could do it at a computational level within a timely manner. So it was furan, benzene, furan, benzene, and then whatever was connecting the two. And so as you can see, I have that in my picture here, where it's a benzene, the connection, furan, connection, benzene, furan, or benzene, connection, furan. So just that repeated, just so we could reduce the system into like a level we could, let's just say, compute within a timely manner. Like, if you wanted...
Okay.
Yeah, if you have any comment against that or for it, or...
I'm just looking at it as you appear to be modeling chemical 8 from their paper, but describing it as if it's chemical 7. And there's some interactions where it appears to be you've taken parts from one model and not parts from the other model. And I'm just a little confused on which one you're actually modeling here.
Well, okay, so
So, David, would it be a fix to your question if Meade would just change the namings, like keep the same, keep all the results, but update the namings?
That would work too.
Okay, I think it is quicker. Okay.
Yeah, I think it's a problem with the name, not with the structure that Meade used. Yeah. Use the right structure, but just the name is the wrong.
Yeah, changing the name would fix it too, in my opinion. Yeah. There's some incongruity here, and I'm just trying to figure out what it is.
Okay.
I do have another question. It's not scientific; it's more organizational to Meade. So,
go ahead.
Thank you. You do have you have presented one isomer, although you probably have two of them, and then you have about 5 types of graphical information. I made notes. So you have movies, you have mass spectra, you have density of states, you have UV-Vis spectra, and you have orbitals. So 5 types of graphical information. And some of the information is, how to say, repeated for different excitations. So do you have a plan how to organize this graphical information, how to make figures for the possible future paper? Because one cannot make more than 10 figures in the paper, and you already show more than 10 slides. So what is your strategy of organizing your data? Maybe skipping some non-necessarily part, maybe assembling, like what is your vision?
The vision, okay, for reasonable purposes, is to look at obviously other papers that have been produced and kind of comparing with what visualization tools they did. So, for example, one paper showed all the orbitals, and they related it to each position on the density of states graph that I've shown here. So they'll show the figure with it, but that total will be one big figure itself. Like you said, well, you can have less than 10 figures total. So the one would be to show kind of what exactly orbitals and it relating to the density of states graph. So that's like one important one. The information I have shown is just kind of like the results that we have currently. And so it's not been, let's say, siphoned or groomed properly. So I would take highlighted portions. So for example, just as a quick view here, I see a highlighted portion of its high peak, as well as it has a large amount of fragments, as you can see with 112, 116. And so I would highlight information about that particular case if we find out that it is reasonable to do so. Mm-hmm. But in particular of saying getting rid of what particular things to get rid of, I wouldn't show each individual mass spec. I wouldn't show each individual video. I wouldn't show each individual bond cleavage. That is something I would not do because I haven't had time to analyze that far yet.
And you were thinking about adding the type of information number 6, the bond length as function of time, right?
Yes.
Okay. Okay. I've got my questions. Are there more questions from any of the group members, visitors?
I have a question.
Please.
Okay. So, this is a kind of a general question about depolymerization. This particular structure, or ones that are similar to it, do they depolymerize in the same fashion every time in reproducibility studies? Or do you know that?
I would have to see how many times this paper, let's just say, depolymerized.
His reproducibility is going to be important when it goes to commercialization. So that will be interesting to see, because you got to think about PDI, right? You got to think about how this is structured. Does it have the same molecular weight each time? How is PDI measured? You know, how do you get the same PDI each time, right? That's important, right? Correct in this case?
Yeah. If you know, that obviously on its own is a whole other, like, let's just say, project.
But it's consistency. You want to make sure, like if you can connect to what you're doing, to what, you know, because you're synthesizing this, right? You're making this, right? Or you're taking it, but you're analyzing it, but you aren't making it, right, in the beginning.
Someone has made it.
Has been made.
Yeah, yes, it has been made. Yes.
So did they do those studies? Did they look into that, or you're not sure?
Yeah, off the top of my head, I'm not 100% sure if they were able to continuously reproduce it many times.
Right, so it's good. But it's important though, because when when you go to apply it and commercialize it, it's good to look at, is it work like you need to every time? So
yeah,
just
I would have to relook at the paper, but just as a position that I'm in, you know, if they redid it twice and it turns out to have very similar, let's just say, products, or, you know, PDI, like you said, then I would say it's okay for us to, at least at a research level, to continue this work, or at least say, okay, it's been reproduced and it did work to be that way, so it's okay. But when you're, with what you're saying, with like commercializing, yes, that would, you know, what the statistical rule is 30, so got to redo it 30 times for like some sort of commercialization of some sort, but that wouldn't happen in a research setting.
Okay.
Yeah, I would say that's an important question. That's kind of a next step. So right now, what the Meade is investigating kind of just the structural features that influence on the degradation. All these processing related things, that's kind of next step, and it's not related right now to the current project.
Okay. Let's make one more call for questions. Dr. Han, Yulun, do you have questions to Meade? No? Okay. So more questions 1, more questions 2, more questions 3. Okay. Congratulations, Meade, with great presentations and discussion session. Let's thank the presenter. So next 3 meetings we will have. Next meeting there will be invited speaker, a student who on solid electrolyte. In 2 meetings, hopefully, Aaron will make an update on coexisting polarons, and in 3 meetings, we'll try to arrange knowledge transfer session on spin orbit coupling in VASP. So with this, I would like to thank the speaker and all participants of the discussion. Special thanks to Professor Rasulev for supporting this collaborative, interesting research. And
thank you.
Thank you.
Thank you for all this, for leading that project, actually, because that's the main contribution comes from you and your group, you who, you know, helped a lot with the coding as well of this new code to get the transitions, the other stuff. So thank you. That's important.
Okay, I think meeting is done. Everyone is welcome to disconnect.
Mm-hmm.
And
yeah, Mal, good to see you. So I'm really happy for your achievements. Yeah.
Thank you. It's good to see you too.
Thank you.
Yeah, no, we hope you guys are staying safe. It's crazy in the States right